Junyu will be talking about MarQSim, which is this tool for reconciling determinism and randomness in optimization and simulation.
Can you hear my voice?
Right, Junyu.
Okay, thanks. Thanks for the introduction. I'm Junyu, and currently I'm a first-year PhD student from the University of Pennsylvania. And this summer I'm working at Lawrence Berkeley Lab. So today I'm going to present our recent work, MarQSim. So this is a compiler optimization framework that integrates the strengths of both deterministic and randomized compilers for quantum Hamiltonian simulation. And this is a collaborative project with AWS Quantum Technologies. So first, let me give some background about the quantum Hamiltonian simulation. Here we have a target Hamiltonian. It can be decomposed into several localized Hamiltonian terms, which is represented by the capital Hj here, with coefficients small hj. The evolution of this target Hamiltonian is given by a unitary matrix U, which is equal to e to the power of minus iht. A compiler can map this evolution onto a quantum chips. In practice, these capital Hj are usually polystrings, which can be represented by a tensor product of poly operators, here shown as sigma 1 to sigma n. And for each polystring, we can have a unitary evolution, which is unitary j equals to e to the power of minus I hjt. This is the basic building blocks for quantum Hamiltonian simulation, and there exists standard compilation process that can map this unitary onto the quantum circuit that we, just like we show on this graph. And now we are going to show the two state-of-the-art compilers for Hamiltonian simulation. The first category is deterministic compiler. The strategy of this kind is trotterization. So instead of implementing the whole Hamiltonian at once, we implement each Hamiltonian term with a much smaller time segment, delta t. And then we concatenate them together to approximate original evolution. Usually the order of Hamiltonian terms is flexible, but will be fixed for a certain instance. We can define a trotterization steps equal to the total evolution time over the evolution time segment, delta t. Here is a circuit example. We can implement the first Hamiltonian evolution in the red box and the second Hamiltonian evolution in the blue box. And in the middle, in the yellow box, there is some opportunities to have gate cancellations. And a lot of research papers have studied this problem. The second category is a randomized compiler, with QDrift being a representative example. In this approach, we will still deal with these short time evolution terms. But unlike a fixed order implementation, the terms are now sampled from a distribution. This distribution is determined by the magnitude of each term's coefficient in the overall Hamiltonian. Terms with large coefficients are more likely to be sampled and executed. One key advantage of this randomized strategy is that it achieves a symptotically lower circuit depth compared with the deterministic Hamiltonian simulation method using trotterization. To summarize, we have two types of Hamiltonian simulation compilers. The deterministic compiler, which is optimized for gate cancellation, and the randomized compiler, which offers a symptotically lower circuit depth. The goal of this project is to combine the strengths of both approaches to achieve a more efficient quantum circuit implementation for the Hamiltonian simulation problem. Before talking about our techniques, we begin by introducing some key concepts used throughout this paper. The first one is Markov chain process. We consider a sequence of random variables, xt, where t typically denotes time. And these variables represent the state of the system at different time steps and take values in a state space S. A process is defined as a Markov chain if the probability of transitioning to the next state depends solely on the current state, rather than the full sequence of past states. This is known as the Markov property. If these transition probabilities remain the same across all the time steps, the process is called time homogeneous, meaning the transition rules are time invariant. To capture the probability compactly, we use a transition matrix P. where each entry Pij represents a probability of transitioning from state Si to state Sj. This matrix encapsulates the full dynamics of the Markov chain. And the next thing we are going to introduce is the example of the Markov chain process. So here we have a graphical representation of the Markov process. In this graph, each node corresponds to a state in the state space. And here we have 4 distinct states. The edges between nodes represent possible transitions between states, with the associated numbers indicating the transition probabilities. From this graph, we can construct the corresponding transition matrix P. Alongside the transition matrix, we will introduce another concept, stationary distribution, a probability vector pi that represents the eigenstate of the transition matrix P. In other words, it satisfies pi times P equals to pi. For this example, the stationary distribution can be easily calculated by solving an eigenvalue equation. Now we are going to introduce the concept of minimum cost flow problem, which also called MCFP in this project. This problem is defined by a flow network represented by a tuple V, E, C, S, T, where V is the set of vertices, E is the set of edges, C denotes the capacity on each edge, and S is the source, T is the sink. In this example shown, we highlight a flow from node 1 to node 2, denoted as F12. This flow must respect the capacity constraints, meaning that the absolute value of F12 is less or equal to C12. Additionally, each edge is associated with a weight, in this case W12, which represents the cost per unit of flow along that edge. So the objective of the MCFP is to determine a valid flow that minimizes the total cost, computed as the weighted sum of all flows across the network. Okay, with these two concepts in mind, we can introduce our techniques. First, I'm going to introduce an intermediate representation we developed for the Hamiltonian simulation problem, called the Hamiltonian Term Transition Graph, or HTT graph. The HTT graph is a directed graph where each node represents a Hamiltonian term, and the edges capture the transition probabilities between terms. To interpret this problem, consider we approximate a quantum evolution by sampling individual Hamiltonian terms. And then we concatenate these sampled Hamiltonian terms and together to approximate the total evolution. For instance, at step k, we might sample Hamiltonian terms e to the minus IH1. To determine the Hamiltonian term for next step k plus 1, we refer to the transition probabilities shown on the outgoing edge from the current node. So from node H1, we might have a probability P11 to stay on H1, P12 to transition to H2, P13 to transition to H3, and so on. These probabilities guide the sampling process and ultimately define the structure of the simulated circuits. It's important to note that the transition probabilities in the HTT graph are not arbitrary. They are subject to specific constraints. This is because in the final circuit, we want the evolution terms to appear according to a target distribution shown in this equation. This is defined by the relative strength of the Hamiltonian terms in the overall Hamiltonian. Mathematically, this means a desired distribution must be the stationary distribution of the transition matrix in the HTT graph. By ensuring this property, we can guarantee that regardless of any start point x, we will eventually converge to the stationary distribution. With this structure in place, we can now describe Q-drift as a special case of our HTT graph intermediate representation. In Q-drift, the transition matrix P is particularly simple. Every row is identical and matches the target distribution. This implies that no matter which Hamiltonian term is sampled in the current step, the next step is always sampled independently from the same stationary distribution. Using the HTT graph intermediate representation, we can show that our approach achieves the same asymptotic circuit depth as Q-drift, preserving the core advantage of the randomized compiler. The next question is, how can we incorporate the gate cancellation techniques as a key benefits of the deterministic compilers into the structure of the transition matrix. Addressing these would allow us to combine the strengths of both approaches in a unified framework. So this challenge can be addressed by solving a minimal cost flow problem to derive a transition matrix for the HTT graph that incorporates gate cancellation. In the first step, we consider a valid transition matrix using a flow model without considering any cost of quantum gates. On the left is a HTT graph representation. First, we split the nodes representing the Hamiltonian terms into two columns. The first column, labeled H-prev, represents the previously sampled Hamiltonian terms. And the second column, H-next, represents the terms to be sampled in the next step. We introduce a source connected to the H-prev to each H-prev, and assigning a flow value equal to the target distribution pi. Similarly, we add a sink connect from each H-next node, also with the flow values matching the desired distribution pi. And then we will connect each H-prev node to each H-next node, with edges carrying some flow. For example, the flow from H1 to Hn is denoted as F1m. By dividing this flow by pi1, which is the target probability of sampling H1, we obtain the transition probabilities pi1m. And other entries in the transition matrix P can be derived similarly using this equation. Transition probabilities defined this way form a valid transition matrix, and this can be formally proven. With the flow model in place, we now incorporate gate cancellation information into the edges between H-prev and H-next. Here we only consider the CNOT cancellation, while the objective can be changed to other gates. So this is done in a straightforward way. We assign each edge a weight equal to the CNOT gate number required for transitioning from the current term to the next. Using these weights, we then solve a minimal cost flow problem. This approach helps avoid transitions with high CNOT cost during the sampling process, while still ensuring valid convergence to the desired stationary distribution, or the original unitary evolution. And the next issue is that although all the transition metrics we construct will eventually converge to the target distribution, their convergence rates can differ. To accelerate the convergence, we introduce a method called random perturbation and matrix combination. In this approach, we first apply a small random perturbations to the weight in the flow model, generating multiple valid transition matrices. We then combine these matrices using a convex combination. The combined matrix typically achieves faster convergence as confirmed by spectral analysis. As illustrated in this figure, in the figure below, the spectrum of the combined matrix shown by the orange line is tighter than that of the original matrix without perturbation, which is shown in the green line. Theoretically, a tighter spectrum implies a faster convergence to the stationary distribution. Okay, now I will introduce the evaluation part of the MarQSim. First, let's look at the experimental setup. We use three transition matrices to guide the sampling process of the Hamiltonian terms. The first transition matrix is PQD, is the baseline matrix from QDrift. The second one, PGC, is the matrix incorporates the structured gate cancellation techniques. And the third one, PRP, is generated using random perturbation techniques. We evaluate three configurations. The baseline only uses PQD. The configuration MarQSim GC combines PQD and PGC. And configuration MarQSim GCRP combines PQD, PGC, and PRP. For benchmarking, we select a variety of ions and molecules with qubits counts ranging from 8 to 14. Let's start looking at the overall improvements. In the graph shown, the blue curve represents the CNOT count for the baseline configuration across different accuracy levels. The green curve corresponds to MarQSim GC, and the yellow curve corresponds to MarQSim GCRP. On average, we observe a 25% reduction in CNOT count for MarQSim GC and a 27% reduction for MarQSim GCRP. This demonstrates the effectiveness of incorporating gate cancellations through the MCFP formulation. Additionally, as suggested by our theoretical analysis, introducing randomness improves the convergence in the sampling process. As a result, MarQSim GCRP achieves a 8.3% reduction in standard deviation compared with the MarQSim GC. The next experiment examines how different combination ratio impacts CNOT gate cancellation. We present 4 curves in the graph. The blue curve represents Q drift with no gate cancellation, and the green curve corresponds to a small proportion of gate cancellation. And the yellow curve reflects a moderate ratio, and red curve represents the highest ratio of the gate cancellation matrix. As shown in the table, the red curve lies at the, as shown in the graph, the red curve lies at the bottom, indicating the greatest CNOT cancellation. The results clearly demonstrate that increasing the ratio of the gate cancellation matrix leads to a greater CNOT gate reduction. Finally, we evaluate the impact of varying the evolution times for the ions and molecules. And our result shows that across different evolution durations, we achieve an average CNOT reduction of around more than 20%. And this is all the result. Thanks for your listening. And if you have any questions, please feel free to ask.
All right, thanks, Junyu. We have time for a few quick questions.
Hi, thanks for the great talk. I had a couple of questions. One was, I think, do you guys believe that you can use this kind of a framework for accelerating how a simulation of the Hamiltonian simulation on a classical computer, if you're using if you're simulating the quantum computer on the classical computer with a tensor network or something? Do you think like this could be applicable there? And the second question was just like, yeah, sorry, first please.
Yeah, please continue the second question. Yeah. So I will answer the first question. This framework can be only applied to a quantum regime because we are object some metric like the CNOT numbers. But if you are considering apply this framework to a classical simulation, I think you can, for example, you can calculate the GPU times, maybe the GPU times you need to simulate between different Hamiltonian terms and try to apply this as the weight of the MCST. I think the minimum cost flow problems. And I think by applying this metric, you can using this framework to accelerate your classical simulation. I think it's possible.
That makes sense. That makes sense. Thank you. I think the other quick question was just, how do you guys think of like this being applied on like quantum computers which are basically doing time evolution directly, which do not have a circuit abstraction and so on? So like,
could you rephrase your question again?
So I was just asking, like, how do you think this would work with a D-wave-like system? Is basically my question. Where you just
you mean D-wave?
Yeah, that kind of a hardware.
I mean, this only applies to digital quantum computers. I mean, for D-wave, they are analog quantum computing paradigm. It's different from this one. I'm not pretty sure how to apply this to their device.
All right, that makes sense. Thank you.
All right, let's thank our speaker again.
Okay, thank you so much.